Okay, we'll keep going with discriminant analysis, and the lecture file is called, I think it's 16 discrimination and classifications. And let me see if I can find it in. Yeah, it should be listed as 16. Yeah, discriminant analysis. Okay, and I will update if I add any stuff in there, and some of the writings is not critical, uh, because I think you guys can find better example, better argument uh, in just Google. Okay, and what I would like to uh, ask you to think about is this. Okay, discriminant analysis and optimization, are they uh, similar? In what sense?
So you can kind of develop a threshold for predicting
Mm-hmm.
based on your x y variable, what have you. If you have a certain x, you can reasonably assume with discriminant analysis it's above or below.
Yeah, and I have confess my background is not operation research or optimization, but I always like to tease my buddies. Dr. Shu Cheng Fang is my office neighbor at NC State. He's a Top Gun OR guy, or sometimes even challenge Dr. Lim. I said, today I can have a lot of situation. I have no clue what's going on. I asked expert, give me some X and some Y, and said this is how they see things, and maybe I can do some simple regression or whatever, and then I just Monte Carlo all the possible situations I can think of, and then just run for you know well however whenever you say stop, you have to give me the answer. I stop, and then can I bubble sort the answer from good to bad, and then I can just have a scorecard. Okay, and well, maybe I can show you this in a very simple way. Okay, I have a bunch of X. I don't know, X1, X2, but then at the end I have a Y, and Y is my performance, and then I just says that my performance got a scorecard. Okay, and let me just times this, and then have this run till say 200, just for now for fun. Control V, and then Control C. Okay, I just run this. I don't know. It could be very, Dr. Lim probably will ask you guys use Garabi or whatever and run the whole things. When it's done, I just said that, hey, give me a bubble sort. No, show me everything you got. Okay. And then once you have everything's, and I can do this, I can have a scorecard. And you guys know, since I'm using random normals, it doesn't look, there's two monotonics. What I really would like to see is, okay, uh, after you're looking at this, okay, what will be the type of things you can do? Can I say that I only care about this top batch of answer? And then once I have the top batch of answer, can I say that, okay, uh, what do they have? X1, X2, or X1, X2 combinations of something. So, or X3, X4, I don't know how many variable causations they involve, but sooner or later, discriminant analysis becomes a filter process and said that, give me some good answer. right? And I even argue that sometimes, of course, that shouldn't be the way how we make friends. We should make friends based on our personality and everything. But in business world, people make friends with whom? Those top guns. You copy their style, you copy their way, and then hopefully you can use discriminant analysis, turn into a causal structure. And of course, you can build this immediately into a table. Okay, this is Top Gun. You consider Top Gun. This is ordinary. And then you have all kinds of combination x1, x2, x3 equal to something. So every one of them basically almost like a factorial of treatment design. And then once you have all this, what you're trying to figure out is that do I have certain combinations? I can bet my life on it. Whenever I have x1, certain things, majority of them will be in Top Gun group. Few, very, very few, will be in ordinary groups. And that will be the recipe you're going to use to become a Top Gun. And then statistically, what you don't want to see is that, okay, everything is possible. If everything is possible, what does that mean? That means there's no secret recipe, or there's no benefit of learning this and come up with this approach. Okay, so I want you to always keep this in mind. Discriminant analysis, marketing, finding the good product, bad product is important, and the procedures, must be science. Identify variables that discriminate best among groups. Okay, uh, the language sounds like statistics, but it got that operation research in mind. And then, of course, you basically said that, okay, I want to be in the green group, or I want to be in the blue groups. And so you can consider that there are marginal mountain signal detection, marginal mountain discrimination signal detection, or you want to have a combination of the two. And when you have the combination of the two, there are two clouds to separate the blue cloud and the green cloud with minimum errors. What you would like to do is to find knowledge of the cutting line to the center of both, or as far as possible. So you want to find an orientation in such a way. And also, you would like to make sure that, okay, on either side, you can build two PDF function and say that, well, since I have an observation here, I'm a lot taller in the Green Mountain, so I must belong to the green. I feel taller in the Blue Mountain, I probably belong to the blue. And so uh, those are the approach we're doing it. Okay, and so by saying that, we need to have two mountains, F1 and F2. And I know the homework I give you is only 2 by 2, but you should be able to do, well, to visualize. There are could be 5 by 5, 10 by 10, except that with that many dimensions, we rely on principal component to summarize the critical one. And the second thing, what we would like to do is uh, let SAS do the matrix computation in the background. Okay, but this in a multivariable sense, you need to know how to build a box based on eigenvalue and eigenvector. You need to know that that box represents the volume or the total amount of variations of each mountain. And you know that that box is the covariation structure, or standardize it as a correlation structure, should be able to tell you the height of the PDF. Okay, and for online student, I cannot see you nod your head, but you have to. If you cannot visualize all this, uh, you're in big trouble, or I'm in big trouble. Next, okay, two populations. It's very easy to say the following. Okay, probability belong to the pi 1 or pi 2. So I can have 50 good products, 300 bad products, or 300 good products. 5% of bad. I'm sorry, what was that? Yeah, 5% of 3,150 bad products, and three among the 3,000 total products of the good products. And so you can have your initial probability, and then you have the correct classification. The probability belong one, you said is one, or two, you said is two. Given is from one, given is from two. And you will be in trouble if it's from two, given is two, but you said is one, or given is one, you said is two. Okay, and if that's the case, we can have a cost of misclassification, and this is what we call ECM. And I kind of like rather than doing it this, we can have the reward added in. Is I can have some reward for correct classification, but right now, if we're only focusing on making mistakes, I would like to minimize the mistakes. Then the expected cost will become given as one and is one, but I said it's two. And then there's a cost associated with one classified as two. Given as two, I classify as one, and then there's a cost associated with it. So this is a pretty straightforward condition expected value of conditional probability. And when you do this, I can, if anyone want to use MATLAB, I have a MATLAB copy of this whole thing, but I prefer using SAS. Okay, and then when you do this, okay, you need to build two mountain, and when you try to build a two mountain, technically speaking, you can have one mountain is very narrow, high kurtosis, very narrow, uh, tall mountain. But you can also have a mountain is very flat. But if that's the case, probably uh, just by itself, you can tell the product is very different, and then you cannot pull the covariance structure. But if you feel the two mountain is pretty much like this one, they stretch in a very similar way, their orientation in a very similar way, then this is the benefit of pulling it. It can reduce computations and come up with more generalized where should I make the cut. And but the way how I play with this is, since SAS is cheap this day, sometimes when I do it, I just say that, hey, let me try to pull, let me try not to pull, and or let me try to pull or not pull based on how many samples you give me, and then to make the decision. And how do I make the decision? Two things, right? Make as few mistakes as possible, and make the total cost as low as possible. And in this kind of approach, okay, job interview, people will say, then how do you know you got a reasonable approach? Then I'll say using nfold, tenfold, or fourfold, the approach. You have a lot of data, randomly divide them into two groups, training group and testing group, or turn them into group A, B, C, D, and then use A group, pull, not pull, and say, hey, see, for A group, not pooling. I got a very good uh, minimum cost. Compare with every one of them. And then if you see that no matter what kind of modeling strategy you come up with, since very consistent, then I will just stick with that procedure. And in the uh, in the old days, people would say, "Well, this is irresponsible of doing stuff." But what I found that right now, in practice, I don't care transportation, banking, any industry. The market change, the market dynamics, the products supply chain change very very quick. So what you consider is the magic bullet last year, last month, would you bet your life on it and keep using it? So a lot of time, how you come up with the decisions, you basically said that okay, I would like to learn from the history, but at the same time, I would like to try the new way, and then in information theory or in in the information theory, I talk about KO divergence, means that, okay, seems like there are certain things, my distribution, my assumption of the world, still the same. Then I'll keep it as it is. But there are certain things, since I have no clue how to build a mountain, and just let me try whatever available and then figure out almost like a voting mechanism. Do you think you always make the decision in voting? You always vote the best candidate? Maybe, maybe not, right? And so you might change party, change your political view or something. In voting, is the same things. Here, we're just basically saying that, okay, let me try everything I know. Use whatever history I can recover. Let me use whatever available data. And then when I try different approach, given what I know and what I learned, uh, you know, this is probably the directions or assumption I should pick. And since SaaS is cheap, R is cheap, you can do that even daily, and then make decision that way. Okay, updating your assumption uh, is important. Okay, next. Okay, so we can also do a uh, ROC curve based on different assumptions. So, for example, this is a very famous machine learning, data mining, cloud computing example. You guys probably do this. 3 different iris flower, and then have you have this in your R course? No. Okay, I'll show it to you. And in this 3 different flower group, I can just basically first do this. I assume there are certain percentage, and then I can decide if I want to pull or not pull, and then to decide what is my poor ECM versus a non-poor ECM to decide.
Where you had the pull the sequel.
Oh yeah, yeah.
Okay.
Okay, let me show you the example. It's right here. Okay, so I think the example I'm using the is IE 55344-A SAS, and I copy from the SAS code. Okay, and here 3 different type of flower species names: Setosa, versicolor, and virginica. Okay, and then first thing first is let's not do the plotting first. Let's just play with this whole things. So here, look at here, the reading format. Here's data line. Okay, first there are four things to read: sepal length, sepal width, petal length, and petal width. And so every time you read this four measurement, and then you just it will tell you if it's flower one, flower two, or flower three. Okay, and uh, the was the and ampersand means that you're reading this 1, 2, 3, 4, and then species, and then 1, 2, 3, 4 in species. The reason we're using ampersand, so we can just keep reading it. Otherwise, the original data set's supposed to look like this: 1, 2, 3, 4, 4 reading. What kind of flower you belong to? Oh, even I do it this way. It could uh, no, for example, I can have someone is reading 2 column, 2 row. I mean two sample and then return, and sometimes 3 sample return. Doesn't matter, and it will just read it. You guys can experiment this if you want to. It's just show you. You read tons of them, and then once you finish reading them, okay, you do a procedure called. And of course, you can always do this proc print to double check the data uh, reading is correct. Okay, and here I'm not doing it. I'm just let you know you can do it for double check. Okay, next. Okay, once you have the data is done, you start. You have output statistics, and then you can have your variance, covariance read, and p covariance and w covariance. I'll come back to that in a sec. I would first. Uh, oh, you guys, would you like to have the? I have the old PDF of SAS discriminant procedure. Uh, it's pretty much the same thing as the one you can check from SAS help desk or support center. I'll upload it. For me, sometimes I like to read almost like a book. It's easier for me to find the material. Okay. Now, so far, so good. Okay. So discriminant analysis, and then after that, their method, normal, non-parametrics, and here is the pool of the test. Let me add a couple in here. Okay, you can have pool equal to proportional. This is where I copy from. Oh, sorry. Priors equal. It's equal. Prior is proportional, and then priors is flower 1, flower 2 equal to certain. 30%, 30%, or 1%, like that. Follow? Okay. So here I can have. Oh no, I did it wrong here. First, pool can be yes, and pool could be no. Or you can say, hey, do the pool according to whatever you want. And then here's another statement I would like you to keep in mind is prior. Okay, that looks ugly. Hmm. Maybe I should explain. You guys see the difference? Is semicolon used to break the line, right? So if I use just one comment here, comment out the whole things, see the second comment is not pool equal to no is not coming out. So if I use this slash star star slash, means everything inside will be, and then you're gonna do the same things slash. Okay, here is another one I'm gonna do for prior equal to uh, equal, means 30%, 30%, or priors equal to proportional. Okay, and so far those are the things we can do, and then after that you can show the distance. That's for the knowledge, and you can show the ANOVA, MANOVA. It's the portions that you can explain and not explain. I'm going to show that in a second. And then list the error and cross list, when I make the mistakes. And those are the options. And I will say at most, I can just give you the lip service about those terms. Why? Because the clear definitions for each one of them, you can find it from their support center. You just put that word in, it will do the computation for you. And you just need to read the definition and figure out how those terms can be used. And from the purpose of this class, I'll say that a lot of time, put those things in appendix of your term projects or uh, your report. The main course for me still, uh, well, if I do this, do I make less mistakes? Do I the cost of my ECM can be lower or not? If I cannot cut down the cost, if I can tell you there are 10 different ways to explain my mistakes, do you care? Yeah, and so that's the whole idea we're doing this. Okay, so after that, you can have your species, and then uh, the species based on these four terms. Okay, and I think in the old days, people play with just here. They will do the following. I'm gonna only using the sepal lengths and petal lengths, or I'm only using one variable to decide everything. And of course, if you only use one variable, you'll make tons of mistakes. But you try to figure out that, okay, but then which one should I use? And then after that, you would, the question, the challenge is coming. Say I'm using petal lengths, sepal lengths, I got a good answer. Okay, then after that, which variable should I use to separate the good product, bad product, who's gonna buy a computer, who's not gonna buy a computer? You check the correlation structure, right? If it's highly correlated, means what? I know one variable, I know the other variable. It's not as useful. And then from an information point is what? Uh, you want to make sure that there's a little independent information beyond. So what does that call? The information gain, right? I gain something by doing this. So it's not in the discriminant analysis, but once we finish the discriminant, we're going to go back to the information theory. And you should always keep this in mind, is that how many variables should I use? If you just want to make things correct, even I give you a set of random number you plug in, probably it will do something at the beginning for the given set since you're fitting it. But you should do the info analysis and figure out that whatever that variable makes sense, it makes sense in every fold. And also you should make sense, try to evaluate is the following. Okay, do I really need to keep this to run the procedures? I know that when I started my jobs in industry, uh, the Japanese company still talking about lifetime employment, but American company usually every 5 years, 6 years, they will have a major layoff, and the company consider attritions is beneficial. And so every time it is said that, well, I want you to cut out 5% of your manpower, Simon. And then they said, this is a policy. I don't care you like it or not. And what company basically tried to figure out is that, Owen, can you take care of Simon's job? If you can, I'll give you, 10% or 20% of salary increase. And the interview, the questions is arranged in that way. It's almost like trying to figure out each variable. Can you provide something other people cannot provide? And so at the end, it's ugly. Who will be out? The one who knows all the information, but everything can be replaced by somebody else or by some other variables. Yeah, so it's brutal, but I want you to think about discriminant analysis. It's about optimization. It's about weed out something. Oh, I can use only three to explain everything and with very good accuracy. Why should I use four? Yeah.
So it's just greedy algorithm.
It's greedy and is a very shrewd uh, greedy algorithm. So not only you're greedy, you also kind of like plan with several layers of trade-off and considerations. So it's yeah, the example is that buying computer using one variable, using another variable. Do I get any benefit? If I do, among all of them, which one I can gain the most? And now you combine the two using the three, and so you even have that Venn diagram in mind all the time. Uh, so have you ever heard this? Oh, so and so has been in the company for 50 years. He knows some secret uh, recipe nobody else know. We cannot get rid of him because of that, especially in manufacturing. We have some very, very old machine. And we got that in the 80s and still functional. We only have one guy left know how to operate that. And so usually that's his job security. But do you think that's good for the company? No. Yeah, go ahead.
At the same time, it's also not good for the employee either, because
Hmm.
you're going to be stuck in one spot because you know something that
Nobody else know.
right. So
Hmm.
your the ability for you to move up will be restricted.
Yeah. And a lot of time when we have a society, everybody is a culture. Everybody is replaceable. It's not a bad thing. Yeah. Okay. So yeah, well, I hope uh, you guys have a cheat sheet or footnote somewhere saying that classifications and an essay question you don't need to turn in. Ask yourself why discriminant analysis can be used for optimization in what way. And two is that if you want to minimize the error, just keep adding more variable. Is that really the right way? Okay. So once you do that, let me get rid of my printout. And oops. Here we go. And you can run this whole procedure. It will tell you every variable, okay, under every conditions, what is their length, septal width, okay? And the most important things right now, oh, here, since the proportion is 1/3, 1/3, 1/3, so the prior probability is 1/3, 1/3. Okay, and I only have 150 observations, so it's 50-50. Okay, and then the second things you can look into is within class. Okay, uh, uh, covariance structure. So I have setosa, 50 of them, so I have 49, and then I can have their covariance structure about their length, width, and for each one of them. Okay, and why this is useful? Well, for one, just by looking at it, septal length variations is 12. Covariant is septal versus septal against myself is 12.4, and over here it's 26, and over here is 40. Let me just look at this. Hmm. One more time. Okay, that'll look narrow enough. A lot of time I would just do this, okay? I'm pretend I know nothing about this set of data. Covariance structure or correlation structure is the first things you can get, right? So just by looking at this, forgot a title. Okay, and Virginia. Okay, what can you do first?
Right now, this is the
Covariance of 3 different flowers.
put them to Z-score and then
Let's not worry about the turn them into correlations. I know you can do that. What will be the first things I would like to compare with? One thing I can do, a lot of time I can just do this. Okay. Equal to this guy's minus this guy. Oops. Okay. And when you using one minus the other one, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. You see everything's is constantly negative, except a little bit here. Or you see something is constantly positive. What does that mean? That means I'm spreading out more than you do. That's why my variance and covariance is always bigger than yours. Would you agree? And so whenever you see a bunch of values, always positive, positive, always positive, or always negative. Well, because I'm using the first one minus the second one, so you see the value is it's like this. But I could have the second one minus the first one. It's all positive, positive. Then whenever you see a consistent set of value, it's all you know. Look, close to 20 positive or close to 20 negative. Uh, a lot of time, that is the how come I have 6 variable? I thought I only have sepal, sepal, pedal, pedal. Oh, well, let's just leave it uh, as sepal length. Okay, let me go back to SAS. I only have 4 variable. How come I end up with 1, 2, 3, 4?
Second.
Oh, now I know what mistakes I make. Okay. Ignore this. Let's come back. Uh, okay. So let's rerun this. I should have a star here. Okay. And let's rerun this. I'm only interested in I know this is the table. You guys really care. Setosa, 50 of them. How many Setosa got classified into the other two? None. Versicolor, 48.2, 149. And so mistake makes are those two. And I'm actually trying to cheat here and try to tell you that a lot of time you don't know the answer, but you can speculate the answer just by looking at the covariance structure. If something is always a lot bigger than the others, and the other two kind of like very, very close together, you know that that flower probably can be, it'll just look, it's big. So you know that's a very, very uh, different type of flowers, right?
So, what you were doing in the previous example, you're comparing the covariance of each other.
I'm gonna redo it so you see where I'm doing where I got my stuff from. And this time, let me see if I can redo it. This in a okay. Let me do this. Okay, so now I'm only have 4 of them. Uh, I was a bit confused why I got 6. Now I'm trying to just ask you not to just copy paste my SAS. You just think about it this way. Back to my this chart. If you see there are 3 mountains, okay, and let me use Excel. PowerPoint. suppose you have two mountains, and then you know that the third mountain is way here. Let me just insert a shape. Say I have a third mountain. It just looks much bigger in the covariance and invariance structure. Okay, and what you don't want, of course, is if the center are very close, then you're in trouble. But on the other hand, you can easily tell if they are not close to the center, everything is bigger. That's why a covariance variance structure looks very different from the others. Then uh, so what I'm trying to say is that even though I tell you you should just sometimes use this in the okay, again, well let me finish that. And then, of course, the last one is this one minus this one. The second and third. Okay? And just by looking at the table, you can tell there are this 28, 27 huge scale, and the one was the small scale. It's happened here. Okay? Now, you should develop some strategy to separate three mountains. But if I tell you that I would divide and conquer and said that, okay, let me figure out there's a one very different from the other two. Let me take that out and then uh, deal with the two very similar and using a different strategy. Just by looking at this and argue potentially the problem can be uh, divide and conquer, not trying to find a discriminant function to separate the three, but doing this kind of, well, it's a different scale. That one in one family, the other two probably in different family. Would you agree with me? You can speculate that way. Yeah. And why this is important is that whenever you're doing optimization or uh, discriminant analysis, whenever you deal with multiple comparison or multi-objective function, and there's no free lunch, right? You gain more for one thing, you lose the resources for the other things. So how to separate a big problem into small problem is always things you should come in your head for any system engineering type of deal. If you don't know how to separate a big problem into a small problem, uh, a lot of time you're gonna get stuck and have difficulty to start the analysis. So what I'm trying to show you here is that a lot of time just looking at the plot. When I'm in a field, I like to do the plot first, mean variance, and figure out the structure. Where's my first cloud? Where's my second cloud? And where's my third cloud? And then if, of course, if this is the case, then I know that I need one more here, end of the story. But if that is the case, trust me, you probably not gonna get too much Christmas bonus or gain too much respect from your customer. Uh, what will be really fun to see sometimes is something like this or something like this. And then how can you figure out a way to take one out and say, oh, this is very different. Let me have this two analyze first. And this is the reason why your homework, your projects here, I would like you to only deal with the two confusing one and said, can you separate uh, I don't want you to work too hard on Setosa. I want you to work on versicolor and Virginica. Only those two. So in the SAS, you can do is this. Let me go back to SAS. Okay, for that problem, I will say go to data. Okay, input if species equal to 1, then delete. Or sure, you can do this in Excel and just separate the whole things. But if I do this, you only have two data sets. So let me do this. And let me. Oh. Okay. So now you only have two flower. Next, I would like you to think about this. Okay. Once you have only two flower, okay, just play with those two flower for now. Okay. I can I'm going to do this manually. Okay, so I have septolangs, everything's here, right? And then I have the species. So if, let me do this, insert. No, I'll do this. Sort. Trying to give you the old homework one more time. Okay. Okay. Now I have 50 observation of versicolor. Agree? And 50 Virginica. Agree? So let's just pretend that's the world we have. Okay. Now let's go back to here. Okay. I want you to have 90% versicolor. You spend 90 of them. Let's just say that 50-50. So 25-25. Yeah, yeah. So let's just do it this way. Let's have a sampling strategy. Okay. So the first one is 90% from here. So if a random number is greater than 0.1, okay, and then your answer will be 1. Otherwise, will be 0. Okay, so if I do this, I have a 90% versus 10% going on here. So here, versicolor 90%. And then Virginica will be 10%. So I'll just do this. No, Control C, Control V. But this time is if less than 0.1, I'll say 1. Otherwise, I'll say 0. So what will be my sample? 90% from this one, 10% from the other one. And you can do 80, 20. Can you do that? 50, 50. And then every time when I do that, okay, can I have a statement here, prior, proportional. That means what? Give me your a priori P1, P2, depends on how many sample you give me. Then using this, can I build a two? Well, let me build one so you can see it. Prior is proportional. There we go. Okay. So prior, totally I have 50 samples, 47, and so you can see the prior. Oh, this is wrong. Prior shouldn't be. Hold on a second. I did something wrong. We shouldn't have 100 sample. You know what I did wrong? I got everybody still in there. Okay, let me save this as a different name. Save as sample 90, 10. Okay, so here, let me go back here. And do you think you need me to run show this once so you know how to do it? Okay, yeah. I'm just trying. You know, if you feel like this is boring, don't worry about it. So let me do it once. So okay, go back to store, data, store, expand, species, and then 90, 10. No, I should do it the other opposite way. Sort. I should start from 90, 10, and then add level to species. Here we go. Yeah. Oh, I know why. Control Z. You know why? What happened here? I have the random number still in there, so I should lock the random number. Control C. Home. Data. Home. Control C. Paste special value. Lock the sample. So now I have, okay, so I'm only interested in data sort. Start from this and then this. Yahoo. I got it this time. So if I do this, I'm only have 4 and 2 different species. Agree? So let me do here. Okay. And I can do this. And what I should do is here. Nope. I can just get rid of it. Okay. So I only have 2. And here I have this in species. You can keep the ampersand, even though I have everything's in column. You just keep reading it that way. Okay. And then I don't need to have if species equal to 1 delete because I already sampled them that way. So first thing first is let's double check print. And then here we go. Okay. What happened to, oh, I get rid of the species. I'm using 1, 2, 1, 2. That's the problem. Fine. Control H. Versi color equal to 2. And then Veronica, right? Virginica equal to 3. Okay. So now we have a subproblem very similar to the problem we had before. Okay. Let's run it. What happened? Oh. Still not right. Yeah. Let's see. 40. How many ones should we have? We should have about 50 flowers, right? Not 100. Let me do this. Save as. Okay, let me get out, and I think I got too much messy stuff in there. There we go. Let's try. We have 2 different flower, 4 different variable, and why this things keep giving me Let's go back here. How come I still have 100 data set point? I'm only. Oh, did I collect all of them? Oh, I did not. I did not do the sort, huh? Okay, thank you. One more time. Yeah. 9010. Add another level. Species. Okay, let's do it this way. Yeah, roughly we should have 49 to 50 because I'm using only half of them. Okay, so let's go back here. And let's see, we only have very few. Okay, now this proportional will play a role because your a priori is very, very different. I'm trying to make this problem very close to our engine block problem. So if we do this, yeah, totally I only have 54 sample, how many mistakes I makes. And then when you check this, okay, there are different approach to do this. But what is important is that you will see that they will use where's my prior proportional. Here you can tell that argument I have before, just look at the variations. It's not useful anymore. Why? Because you have a very, very biased sample size. And so when your n is relatively 10 times more sample from one side than the other side, the variation is divided by n, then you're comparing orange with apple. Okay? So uh, at least you see that now you need something to help you decide your P1 and P2. So that's the reason why we're using proportional to set up the prior 90%, 10%. Okay, so this is the way how I did my first 2x2. Okay, so let me check with you if you can do the same things. If I give you this example, and well, this is really not too well. Yeah, well, I'll give it to you, but I'm not sure you're gonna make less mistakes if you have this one. But can you see where I'm going with this? Is in your lecture notes. Can I have 90-10? Can I have 10-90? Can I have 50-50? And once you do that, can you have your mistakes based on pulling the variance structure or not pulling the variance structure?
So you're essentially trying to find the error in whenever you partition the data set.
Exactly. And then, of course, at the end, I can tell you what is the cause of uh, pull or not pull, and then you're gonna build your structure that way. So first thing first is okay. Let's go through our laundry list. Okay, you see how I monkey around. Get rid of the largest Setosa because Setosa is a different animal. We can have Setosa versus Virginica or versus play two at a time, but I think play this is sufficient torture. Okay. Second thing is that once you have the four variables, we need to say that I want you to sample this in a different way. And since your a priori is different, you need to put that a priori in your discriminant analysis. And the second things you need to do is plug them in. And once you plug them in, for example, the default priors equal doesn't make any sense anymore, right? So even the comparison of the covariant structure doesn't make any sense anymore. And then we use priors equal to proportional. And in the lecture notes, you can tell we can have priors, oh, species 1 equal to 0.3, species 2. You can specify that. You can make, destroy SAS by doing what? 90% of the sample from Virginica, but I say a priori 10%. Now you're gonna confuse the whole eigenstructure into a different nightmare. Okay, so finally, let's go back to the homework. So pool so far in SAS is easy. All you need to do is just pool, not using tests. You just say yes for all of them, and or say no for all of them. Then you're gonna have 10 sample yes, 10 sample no, and finally, okay, uh, for each one of them, can you plot the ROC curve by using those 2x2? And can you, if I give you the initial cost, unit cost of every mistake, you have this, can be calculated. You have P1, P2 given by the proportion, and I tell you the cost here. Can you figure out the expected cost for each one of them? And then, of course, you can use that to say that I have two quality inspector, one using pool strategy, one using no pool strategy. Which one is cheaper? And the second things I can ask you to do is compare the pool versus non-poolers detectability. Are they pretty much the same level from the z-score, or one is higher than the others? Okay, and if we do that, I you can tell everything you've done. I don't care now the SAS or the problem I give you is not 4 variable, is 14 variable. It's not 3 species, is 5 species, and it's not 150 observation, is, I don't know, big data, how many observations. This toy problem pretty much uh, give you a main storyline, how to find enough to decide how to get into a certain family. If I see certain length, certain height in a certain way, most likely I'm in a good group or I'm in a bad group. And if we got this done correctly, then the homework right next to it is just a bunch of uh, how to manipulate the cloud center, cloud structure, take the log to decide, oh, if this based on the cost, I should classify, cheap mistakes, I can make a few more, and expensive mistakes, try to avoid as much as possible. Okay, and after that, okay, we can find the how to draw the line and the height. For some of the stuff, I probably just lip service and said, this is the way how to do the computation from the SAS output. Once you have that, this output will give you uh, the information you need, and then you can compare the height, compare the where's the lengths. We're done, and we go back to Bayesian network and start playing with the Bayesian net, and that is my plan. Okay. Uh, Question for me? Yeah. It may sound, this homework could be labor intensive, but if you can find a macro to just say random number set one, random number set two, just resort and grab everything's. It's not that, and not to mention, you only need to build those sample because the comparison is one word change, yes or no. Oh, that's the reason I did it here. See here, I said SAS name is yes, 9010. Next one, you can say save as 80-20, 50-50. And so when you finish the whole things, you just said that, let me do all the pool. Yes, 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 yes. So you can very quickly build your 2x2 table. And once you have the 2x2 table done, the rest is just dump it back to Excel and do the ROC curve. I know a book, it's called ROC curve using SAS. Okay, but my recommendation is don't use that approach. Why? It covered too much other statistical assumptions and material, uh, divert too far away from our main system approach. But if you guys want to go Google, you can find it online. I think uh, we don't have a copy in our library, but you can see it online. Okay, and SAS sometimes give their books PDF free away. Okay, since we start early today, should we call it a day? Okay, thank you.